folks, picking up where I left off on this just kind of short math lecture. And I wanted to make this kind of a standalone lecture just to give you a chance to pause and absorb the previous material. And what I also have right here in front of me is a handout that I will make available on Canvas, which will actually walk you through what I'm about to walk you through. I'm going to go through it a little fast. However, if you want to try and absorb that a little bit more on your own, then you'll have access to this document that walks you through what I'm doing. Okay. So recall, we set up here the form of a standard second order differential equation, which basically says second derivative of a function plus the first derivative of a function plus the function itself all equals 0 for the reduced form. Okay. And if we have something in this reduced form like this, so as you might notice here, what we would do to the Schrodinger equation, we would algebraically rearrange it to match this form. Okay, and we're going to do that. So then we use the process that's called ansatz, which I don't think it says it in the document, but this is the mathematical method. And ansatz is German for guess. So guess the solution. Now, as it turns out, not all guesses are made equal. For example, you might guess, well, if y equals 0, then I would solve this equation. And you're absolutely correct, right? If y were 0, that would be a solution. So we can't use that guess. So what we do, and we do this for all standard second order differential equations, we're going to guess that y equals e, so exponential, raised to the power m times x, where m is a constant that we need to determine. And we say that this cannot be equal to 0. Okay? So now we've already guessed that e to the mx is a solution for y. Okay? So now, and that's going to be all of our initial guesses. Y equals e to the mx. So now what we want to do is take the first derivative of this. So dy dx, and because we know m is a constant, that's going to be m e m x. All right? And then we know that the second derivative, we need to do that as well, okay, is going to be m squared e m x. All right? And now what we want to do is plug our guesses back into our equation. All right? So that's going to be, so we're going to supply the second derivative. So that's going to be m squared e mx plus, so perhaps we might have some constant in our differential equation, a. Okay? But then we also have the first derivative, dy dx, is m e m x. So as you can see, we've got a couple of constants we're going to have to figure out. Okay? And then we also recognize that we have this other constant, b, and times our guess solution, y, e to the mx. And then we know from our reduced form, this all equals 0. Okay? And so now what we can do is play a little algebraic tricks. Okay? So notice here we have e to the mx in every single term. So I'm going to divide all of that out and say m squared plus am plus b equals 0. And look at that. We've reduced this differential equation to a simple quadratic where we now know that we can say m equals negative a plus or minus a squared minus 4b square root all over 2. Okay, right? And this is what we call the auxiliary equation. And you notice here this document to the right, it kind of walks you right through that. Okay, so now we have a few things to consider. Let me see if I can, I'm just actually going to just leave this up to remind you this process that we just did. Okay, so now we have a few things to consider, because as you might recognize, when we go to solve M, we're going to have three possible outcomes. So keep track of this, okay? We started with second order differential equation that we put in the standard reduced form. All standard second order differential equations, we guess ansatz, and the guess we use is y equals m e to the mx. We take the first derivative of that, we take the second derivative of that, okay? And, excuse me, we set this up, and this turns out that it becomes into the form of a quadratic. Beautiful. And now when we go to solve this quadratic, we're going to get three possible outcomes: real roots, imaginary roots, or complex roots. Okay? Now you know why I went through complex numbers on the previous lecture. So let's suppose that we discover m equals plus or minus a, where a is a real number. Okay? So this would be in case my auxiliary equation is a perfect square, for example, or has a real number solution. Okay? So then we know m has to be plus or minus a because it's a quadratic. So then remember, we guessed y equals e to the mx is a possibility, right? So now this means my y1 solution is e to the ax, and my y2 solution is e to the negative ax. And because both of these are acceptable solutions, we will come up with what I later refer to as a basis set of solutions where we say y equals some other constant, c1, e to the ax, plus another constant, e to the negative ax. And upon normalization, so if this was my wave function, we would normalize this, and then we would get the values of those constants, okay? So in the event that m just equals a, okay, which is also a possibility if we didn't have a perfect square, okay? Then we get what's called double roots, and that goes y equals c1 e to the ax plus c2x eax. Okay, so those would be our possible solutions. What if we have imaginary roots? So that means, in other words, if we solve this quadratic equation and we get, let's see, m equals plus or minus I times b. Okay? So then my solution 1 would be e to the ibx. My solution 2 would be e to the negative ibx. Okay? And my general solution would be y equals, and once again, some normalization constants that we need to determine, c1e to the ibx plus c2e negative ibx. Okay? And let's see here. Yes. Okay, great. And here's where I want to take a step and remind you of Euler. So recall the Euler solutions. If I write e to the ibx, okay, this can actually, so when we have e raised to the power of an imaginary number, we can actually write this as cosine bx plus I sine bx, okay, which is very cool. If we have e to the negative ibx, this equals cosine bx minus I sine bx. And the reason why all of this works out, this is my favorite equation, okay? 1 plus e to the I pi equals 0. And I love this equation because it's like all of the natural numbers, 0, 1, e, I, and pi. You can actually slam them together all in one equation. Very cool stuff. So in other words, e to the I pi actually equals -1. And I'm not going to prove Euler, but that's where it comes from. So then now, what does that mean? Well, this general solution, y equals c1e ibx plus c2e negative ibx, as you might guess, it's more practical for us to use sines and cosines describing wave functions. So I'm going to write this up here, and this is a general solution, okay? So I'm going to write this as y equals, and I'm going to write C1 prime to note that that's different than this C1. And that's sine bx, okay, plus C2 prime cosine bx. So as you imagine, what we basically just did, so because my general solution says e ibx plus e minus ibx, so we actually have cosine bx plus I sine bx plus cosine bx minus I sine bx. And the reason why these I sine bx's don't cancel is because they're not 1-to-1, right? They're not, the C2 value is not the same for either of those. So basically, when we have imaginary roots, okay, so when we come up with m plus or minus ib, we can just go directly to this solution for imaginary roots. Sine bx plus cosine bx with respective normalization constants in front of them. And so finally, if we have complex roots, so in other words, m equals a plus or minus ib, and we now recognize that's a complex number, right? A plus or minus ib. My solution 1 is y1 equals e a plus, oh, let me start this lower. Okay, so if we have complex roots, I'm going to cut this off here and cut this off here. There we go. Then we would have y1 equals e to the a plus ib times x. y2 would be e to the a minus ibx. My general solution in terms of exponentials would be c1e a plus ib all times x plus c2 times e all raised to the a minus ib all times x. And the way that this would shake out if we used Euler and got this in terms of sines and cosines, which is more useful for a wave function, okay? I'll give you the general solution. It will go as y equals e to the ax times c1 prime, which is different than the c1, okay? Sine bx plus c2 prime times cosine bx. So I'm going to box now all of our general solutions that I want you to kind of keep in mind, okay? Because really, at the end of the day, I'm going to backtrack just a little bit about this, or I'm going to backtrack just a little bit. So I'll remind you, when we get this auxiliary equation and we solve this quadratic, remember, real roots, imaginary roots, or complex roots, okay? We got to see what we get. If we get real roots, and we know that the solution to that quadratic is m equals plus or minus a, just go directly to this, and it's perfectly acceptable to just write c1 and c2 because we have to normalize those things, right? Those things are constants of integration that we have to determine, okay? If we get an imaginary root, so in other words, if the solution to my quadratic is plus or minus IB, just go directly to this thing. Okay, if it's plus or minus IB, it's sine bx plus cosine bx with some arbitrary constants in front of those things. And then finally, if we solve the quadratic and we get complex roots m equals a plus or minus IB, we can go directly to that solution right there. Okay, so how